He's not going to be here. He's like, oh, I really hope I record it.
Oh.
He's going to record the last one.
Yeah, I record every lecture except the ones where we go through the exams.
Oh, right, because
Yeah. Okay, so let's get started. First of all, an announcement. Tim thought that you guys looked extremely tired in the last lab. I thought maybe there was an exam before. Is that true? Or?
Yeah.
Okay, so we decided to postpone the homework deadline for this one, so we can take a little bit of a break. Bad luck there.
No, you have more time for your other classes.
Yeah. So you got another week for this one. We actually have 2 of those spare weeks. I thought we could use one for this, and then maybe maybe we'll vote on how to use the next one. So there's there's what, 5 homeworks left to do, I think, and we have 7 weeks to go, or something like that. Not counting the exam. Okay. What's that?
They
Okay.
changed how console at AWS was.
Okay. Okay, so today we're talking a little bit more about network programming, socket programming, the internet in general, and perhaps a little bit of email. Let's see. So let's start with some drawings. Actually, what did we have last time on here? Yes, so last time we did some just a quick overview of everything that happens when you do a web connection. I thought we'd take a closer look at how the internet is really structured. So today is a little more conceptual, and then perhaps we'll have a little bit of time for basic socket programming in this latter half of the class. So let's start with a network host.
Is it recording?
Yes, this is recording. Although I don't know if it's picking anything up, given all the conversation in the back. Okay, so let's see. So a network host, I guess everyone's very familiar with networked machines these days, because what's a computer without a network? It's pretty useless. But if we want to think about the networking device itself, the Wi-Fi adapter or the Ethernet adapter, there isn't anything particularly different between that and, say, a disk drive. Right? So it's just another attachment to the computer. It doesn't really do anything different. If you want to talk to it, you have to go through the operating system because it's another input-output device, and it's abstracted the same way a disk is abstracted. The application doesn't get to dominate or to say exactly what the disk does. The application makes requests to the OS, and the OS decides exactly how to handle this request. Same thing with the network interface. So you say, oh, give me a connection to this machine somewhere else. The OS will handle it for you, but you don't get to send bits out to the network interface directly. So that's all the same. Everything, yeah, pretty much on the host itself, there isn't anything particular about the network. But if we look a little bit further out, let's say we start with our just to sort of see what really happens in our network. Go a little bit here. So here's our end host, and on there, so that's my laptop, let's say, and on there we're running, say, a web browser. Oh, there we are. Okay, so the browser now wants to make a connection to, say, our web server over here. So this is another end host. There's nothing special about a server, except that it runs a server program. HTTPD is a common name for it, right? So HTTP being the Hypertext Transfer Protocol, D for daemon, a program that just sits there and it's always available to answer requests. So it's daemon, I suppose. I don't know how you pronounce it. It's not the daemon with just an E. It's the other one, which is like a butler, I think. A guy that just is around when you need him. And so the Ds are all those butlers. Okay, so anyway, the question then is what's going on in between here? And in this class, we don't really care that much what's going on. So you could, if you want, think of it. Let's see. So this might ring a few bells. Let's see. I just need to change it to Alright, so we talk about cloud computing a lot these days. And what is cloud computing? It's just, okay, the end host talks to something in here, and we don't know what it is, and we don't care. All right, that's all cloud computing is. So you put stuff on the cloud. What does that mean? Well, it really means, okay, you store something on a server. All right. There's nothing, the cloud doesn't exist. The cloud is an abstraction for a bunch of these machines all over the place. And there's nothing particular about cloud computing except for the fact that there's so many machines. Right? So with the Amazon EC2, that's called a cloud service. Well, you get, as you know, you get to rent some, or in this case for free, borrow some machines over there. But they don't do anything special. And so they're virtualized. And we're not going to talk much about virtualization in this class. But there isn't really a big difference between VMware, running a VMware instance, and what Amazon EC2 is doing. So you're running a VMware instance on one or more of their machines. That's all there is to that. Okay, so most people are perfectly fine with thinking of the internet and all the servers and everything as, if we just talk about layman, it's like this, right? You have your browser and it talks to the cloud, and that's all there is to it. If you're a web programmer or something, then you need to know about this part. So now we actually are running our own server, but we don't really care about what's in between. And for the purpose of this class, it's not that important to know what's in between, but I thought we'd take a quick peek. Okay, so the first thing that happens is we're going to be part of a larger network here. We call this UIC, let's say. So the UIC network typically runs, it's its own little system. Right? So all of the networking within UIC works without having any internet connection. You can cut the internet connection at the border of UIC, and I can still access the UIC website, right? Because the UIC web servers run here. All the communication internally works fine, so on. So this is called an autonomous system. You may have heard of this, AS, or autonomous system. And one of the things that an autonomous system has, which is not the same, so this is not at all the same as your home network. Your home network, you can't do much. Well, you probably can have regular local communication between the machines, but without the connection to your internet service provider, you're not going to get to a single web server, for example. And probably without the internet service provider, you won't even have a proper IP address. You'll have one of those private addresses that you get from your wireless access point. But if you didn't have this wireless access point, you wouldn't have anything. Whereas with UIC, it actually owns a range of IP addresses. So let's take a look at this. So if I go to, and it's a little funny because when you're on a wireless connection, at least within UIC, you don't get a proper IP address. You can see that here. My address is 10.something something. Any address that's 10.something something or 192.168.something, and so another one, 172.192, I think. These are kind of fake addresses. They're fake in the sense that if someone is in, say, Australia, and they want to connect to me, if I have an address like this, they can't find me. They might get to someone else in their office. Right? These addresses are reused in millions of places all over the world. Whereas an address like, basically any other address, that don't start with 10 and don't start with 192.168. So here, bits.cs2UIC review, that's just another machine. It has an address like this, 131.193. Okay, so this one is globally reachable. It's called a public IP address. It's a good thing to know. If you have 10. or 192.168, you can't run a server, let's say, because no one can reach you. Actually, the other machines in your home, or in this case, the other machines on the UIC wireless network might be able to, but it's not guaranteed. If you want to be able to reach other people, want other people from around the world to reach you, you have to have a public IP address, and those are getting a little scarce. You may have heard of this, the IPv4 address shortage. Yeah, I'll skip that for now, but basically there are no more addresses. What's left are people that got too many. So UIC happened to get too many. The CS department got way too many. We had a surplus of about 1,000 addresses until very recently. And UIC, central UIC, they needed these addresses. So what happened was we all had to stop using these public IP addresses for our desktops in the offices and things. We got these fake addresses instead, and now UIC has a few more of the public addresses to use for other things. So that's basically what's happening now. Reuse of things that aren't properly, aren't necessary, so to speak. So someone takes over a little bit from somewhere, and maybe sometimes they pay for it even. I think CS department didn't get anything back for it, but okay. So with IPv4, that's why usually you don't end up getting public IP addresses for your home connection. Certainly, if you have many machines, you only get one IP address from your provider. You have many machines, then you have to put one of these little routers or wireless access points in between, and that then makes lots of fake addresses for you that only work locally within your network. That's for making connections in. Connections out still work, and you'll know why from CS450, I think.
So the public IP address, you get that from your service provider, or you?
Yes.
Okay, so we have one for all our computers then, essentially, at home.
At home, yeah, exactly.
Okay.
Yeah. So you can actually find this out. Look at this. If I say host here, not host, who, sorry. So my connection, that's from home. So who just says, who has logged in here lately? So this morning at 9:20, I was logged in from Comcast. And now I'm connected from this address. So that's not actually an address, that's a host name. But if we say host, resolve that, we see, okay, so that's the address I was coming from, they say. That's weird, right? My address is 10 dot something, right? So the way it actually works is, who's running this wireless network, they're faking all these addresses. But then at the other end, like at the public-facing side of our fake network, there's one shared public IP address, and that shared address is this one. Right. Same thing in my home. None of my machines have this address. Right. This address is only my wireless access point has that on the internet side of its interfaces. On the home side of the interface, it's all these fake IP addresses.
Is it actually your router, or is it your modem that has that address?
In my case, I believe it's the same machine, if I remember correctly. But yeah, the modem typically don't have addresses. If it's a straight modem, it doesn't have an address. But yeah.
So if you want to set up a web server on your home computer, you would use that address 67.167 so that people can actually connect into it from there?
Right. So if I want to run a web server at my home, then what I can do is rip out the wireless thing, put in one machine, and then since I actually got, and I believe I do get, because I pay way too much, I do get a public IP address. So there I would be able to host a web server. Or there's all sorts of tricks. It's called a NAT gateway. There's port forwarding things you can do, so you can pretend that, oh, when a request comes into your gateway, if it happens to be port 80, well, then it should actually go forward to my web server that's happening to sit on the fake inside. Right? So there's ways to do it, but basically you have to have a public IP address to be able to run a server.
At least one.
Yeah, if you want to run two web servers, two different machines local inside, then you have to have two. There's some more trickery you can pull, but to do it for real, you have to have. Is there another question? No. Okay, so that's all of that is an aside. Where were we? Yes. Okay, so we have a nice IP address like this. Now, where did I get it from? Well, we said, or where did that come from? Well, we said the internet provider gives you an IP address. So for UIC, we don't have an internet provider. We're an autonomous system. We don't have an internet provider, but we buy service from a bunch of different providers. So none of those give us IP addresses. We own these addresses. So very different from your home address, which you kind of rent from your service provider. But anyway, so if I now say who is, and this address, oh, come on. Let's try it on a more well-equipped machine. Who is? So here you see the range from 131, 193 to this, from 00 to 255, 255. It's 16 bits worth of addresses is owned by UIC. How many addresses is that? Come on, computer science people. Powers of 2. 2 to 16, very good, yes, but we need the absolute number here. 65,536 addresses, okay? Those all belong to UIC. That seems plenty, okay? So here we see who's owning it, right? University of Illinois Chicago, and we got some people in charge of it. He actually has retired. But I think some other people are still around. Okay, so UIC owns this, which means they are allowed to use these addresses for whatever they want within their local network. Okay. The addresses are actually no good anywhere else. So if I was to take one of those addresses, it's easy, right? In the network configuration, I can just type the address, and then I get an address, right? But it doesn't really help me. It's like saying on my home, right, I don't like my street address. I'll just put a different address on the home. It doesn't work. I can maybe change the number on my home, and I think the postman might respect that as long as it's sort of in the right range. All right? But if I change it to some completely different street name, I won't get anything. Same story here. So these addresses actually only work within the UIC network. The way that works is here, the browser or the end host makes a request, and we're saying, okay, I want to talk to 193, 131, come on, 131, 193, 34. It froze. Come on, wake up. Okay, nice. I think I accidentally hit some fancy Apple button here. And the machine is very tired. Okay, we're back. 34.157. I think that was the address. No, 175. Okay, so say I'm in Australia here with my browser. I have a completely different address. It's not necessarily Australia related, the address, but it'll be a completely different address. Now, there's a machine at the end of this network called a router. And the router keeps track of what's going on the rest of the internet for you. So it has an idea for every prefix. So in this case, it was a 16-bit prefix. And we're saying, oh, this is what's owned by UIC. Right? So anything that starts with this needs to go to UIC. For an autonomous system, you actually have, so there's different kinds of routers. And you can go to Best Buy and you buy a router, and it's not much of a router. But a real router is called a BGP router, a Border Gateway Protocol router. That's what routes between autonomous systems. So in this case, it actually looks only, it has a record for every one of these prefixes. This is called a /16. And it knows for every one of these prefixes where it needs to go in the whole world. So that's just like at the moment about, I think it's about 350,000 prefixes, which are basically autonomous systems all over the place. So now this router in Australia knows where UIC is. So it starts sending it toward UIC. Now, unfortunately, this router, if you're an autonomous system, you have probably a few different connections. And this is not something you can inspect. There's no tool to show what kind of what the connections are between autonomous systems in the internet. So we might have a connection here to Global Crossing, perhaps. That's a popular one, big one. Actually, let's put a different one that's more likely here. AT&T. AT&T has a huge global network. Okay, so UIC probably has a connection to there, but then they also have a connection to this thing called Internet 2, which is not the second internet, it's just a silly name. So this is an organization of university networks that have very fast connections to each other. So there's probably another link going there. Maybe that's it. Let's say that that's it now. So there are two fiber connections coming from UIC, one going to Internet 2. There's a nice hub in downtown Chicago. We have a really fast link to there. And then there's another link to AT&T. Probably another fiber, maybe a copper link going to some office of theirs. Okay, that's all there is. So now, well, now we're going the wrong way here. So say now I want to get to Australia because I'm starting with UIC. So the router here has to make a decision. It's actually sitting on the sort of on the corner here, so it has access to both of those links. And when I say access to, it probably means it actually has those two links going into the machine. A router is nothing other than another computer, but there's one very special thing about a router. Any ideas? Yeah, but a regular computer can do that just fine. I mean, it's really the insides is just a computer. That's not what's really special about this. Most computers don't have what I'm talking about. Blinky LEDs. Now that's not it either. More than one network interface. Right? So a regular computer, if you're lucky, it has one Ethernet interface. These days, maybe it's even 0. This one is 0. But a router, you have to have at least 2. Otherwise, you can't really be a router. Even the ones you buy at Best Buy, it's going to have one coming in, one going out at least. If you're a BGP router, probably you have a dozen or 100 or something like that. So there's, it's not so important how many, but you need to have at least a few. Okay, so this BGP router has a direct connection to someone else who claims to be part of the Internet 2, and someone else who claims to be part of AT&T. So now they've exchanged messages, and this part we can skip. We can leave that for CS450. They've exchanged some messages, so this BGP router now knows, oh, if I get this prefix, let's put some other prefix. Yeah, okay, this is maybe Australia then. And the prefix doesn't have to be 16 bits. It can be 8 bits, or it can be even 32 bits if you want. And that's then specifically for one machine on the internet. But anyway, you have some prefix, and now the BGP router knows, oh, that prefix, I give it to AT&T. Oh, the other prefix, okay, I'll give it to over here. That's all a router does. So it takes a packet coming in, and it sees what's the destination address. Looks at the beginning of it, the prefix, and says, oh yeah, I remember that one, this direction. That one, this direction.
I believe all they do is basically say how many hops would it take me, and it knows the shortest amount of hops is.
Oh, okay, so no, that's not actually quite true. So if we want to talk about routing algorithms, we shouldn't do that here. But there's routing algorithms, there's all sorts of different kinds. One would be find the shortest path. Well, on the internet, they don't care. That's not at all the goal here. So you can think of this as manually configured. For the internet, it's essentially manually configured. It's just that it's distributed. So many people collaborate in this manual configuration. But it's pretty much all manually said, okay, 69.99, go that way. Right. So the router will send it this way, and now what? Well, AT&T doesn't actually have a connection to this Australia dude. So call this AusNet. Okay, So that doesn't work. But maybe there's another company over here, Aus ISP, that's selling connectivity to this this Ausnet, right? And now they happen to have a connection to AT&T. And in fact, AT&T has connection to Internet 2, and Internet 2 has a connection to here as well. And there's a whole lot more going on. But it's not all fully connected. These links here, when I say they're connected, that means there is an actual physical cable going between them. Right, so none of this virtual like electronic stuff. They had to pull a cable. So it's a lot of work. Okay, so you want to go from here. We now decided, somehow the router decided that it goes this way. Then AT&T, it's not actually, by internet rules, it's not allowed to go this way and then that way. It's going to have to go straight to here. And then eventually it gets delivered to the end. And now, of course, the opposite is true here. Now this end host wants to send back a packet to 131.193. Its local router knows, oh, it needs to go this way, and so on. Okay, so that's sort of the process here. So all of these autonomous systems, these are not routers. These are enormous autonomous systems with tens of thousands of machines on them. But at some point, there's a border. So this BGP router says, oh yeah, AT&T is responsible for that prefix. Delivers it here. Inside of AT&T, any sort of magic can happen. So there can be all sorts of different methods in there. They have their own internal routing algorithm, and nobody cares. The internet does not care what happens there. What they do care about is that AT&T has promised that they will deliver packets for 67.99 for this autonomous system. So it will get delivered and then to here, and same thing here, same contracts, right? So this guy has promised to deliver onto there. So, yeah.
I assume there's no guarantee that the route back will be the same.
There's absolutely no guarantee, yeah, and oftentimes it's not. However, it's usually the case that if you send 2 packets, they will travel the same way. Okay, so the routers don't make decisions on the fly. They've already decided, okay, that prefix this way. They've made that decision. They make that decision on the order of seconds or minutes. So if you send 2 packets back to back, most likely they're going to go the same way. Why do we care about that? Any ideas?
Because of packet
You don't want to be out of order. Give the back packaging a shorter route, the front packaging a longer route. Back packaging first.
Yeah. So you could get unlucky. Some packets take a long time, other packets take a short time to get through it, because there are no guarantees, again, about the speeds or the congestion level on the links or anything like this. So you might send 2 packets and the packet that's behind actually gets to the destination first. That's annoying.
So TCP will fix that on a regular basis.
TCP will fix it to the extent that it's possible, which means it'll queue things up and wait for the...
So it's slow.
Exactly. You get the extra delays by that. Basically, you get the lowest common denominator there.
So you're always going to get them in the right order?
You're not always going to get them in the right order, unfortunately. So there's the routing on here happens on, so these decisions are made on a minute or so basis. Decisions in here you don't know. But usually, the reason that you get packets out of order, it's very common to get packets a little bit out of order. The reason for that is this sneaky thing that you can only buy links of a certain capacity. You can buy links of 10 megabits, 100 megabits, a gigabit, 10 gigabit, like those actual connections, right, that you buy from the hardware store. Well, that is the computer hardware store. So what if you want 20 megabit? You don't want to, let's say 2 gigabit here. So you know the gigabit interfaces, they're not very expensive. Many of you have probably seen this. You want a gigabit thing, it's I don't know, $20 or something. Okay, but now I want faster than that, but I don't need 10 gigabit. Because the 10 gigabit, that's crazy expensive. It's like $200 for this interface. So $20, $200, okay. We need a little bit faster. What do we do? Yeah, so we use another one. All right, so now we have a 1 gigabit interface here. and then we put another one here. Okay, so now there's 2 links to AT&T, and the router just knows that, okay, the packet needs to go to AT&T. So it's going to just say, okay, whatever, I'll use this one this time. Next time I'll use this one. And now there's some queues, there's some variable delay on these links. So you might end up sending packet 1 here, packet 2 immediately after on this one. Packet 2 just gets there a little faster. So you get minor reorderings like this all over the place, because it's common to do this, what's it called? It's not binding, it's... No, that's not the word either. There's a good word for it, but I can't recall. Anyway, so this is common, putting 2 links together, and that causes some minor reordering, but that's not a delay problem. TCP can quickly reorder them as they come in. Okay, yeah. Yes, every hardware interface that you will see probably has a MAC address.
But it's still just one IP.
No, it'll be 2 IPs, but it doesn't matter. The IPs inside of here, they don't matter much. From the purpose of the end hosts, and from the point of view of the end hosts, they don't really exist.
I figured because we were talking about how a message gets sent to a certain IP address and it just goes over the route. Would AT&T does have to send it to specifically one line from end hosts as well?
Yeah, you can split things all over the place. Yeah. The only real rule is it has to get to the destination. Most of the time. You're also allowed to drop it if you can't be bothered. Right? So the word for it is best effort service. The entire internet is based on best effort service. There is no such thing as a delivery guarantee. Okay, so maybe one more thing about the architecture here before we finish up. I've been drawing these things a little strangely. So these links look long, and the networks or the autonomous systems look small, but it's not like that. The networks are huge, and the links are really small. So what do I mean by that? Well, AT&T, the network spans the globe. They have their own cables going between their own machines all over the world. And then the link between AT&T and the Internet 2, this is also an enormous network, although it goes only around North America, maybe a little bit extra. Sometimes it goes across the Atlantic. But anyway, so the links, any idea? So I would, actually, you want to take a guess? Let's take a guess here. How long is this link? So I'm saying this is a world-spanning network. Right? But how long is the link between AT&T and Internet 2? You've been guessing so much. Let's have someone else guess.
Less than a foot.
Less than a foot. Damn, okay. That's 100 miles. Okay, we got 100 miles and less than a foot. I like this range.
Do you want to go to like how many inches? We need more specific than that.
Okay, so less than a foot. That's about like that. All right. So you got to have the connectors, and then you got to kind of. But
20 feet.
Okay. So anyone else?
3 miles.
You want to justify this? So why do you think it's over 100 miles?
Because I still think that 100 miles...
Oh, it was you.
I still think that 100 miles is relatively small compared to the size of these networks. So we're still talking relative size. The networks are enormous. 100 miles is nothing. We're
Okay.
talking about, hundreds of thousands, millions of miles of the network, and then just 100.
Okay. Okay. Jake?
Kind of depends where they have. We might have 2 offices in the same city, and we might be across the street from them, so it might be a matter of like being screaming across the alley. Or they might have 2 routers in the same room, which is you can't go from one to the other.
Yeah. Okay. Ian?
Well, you said they had tens of thousands of computers. So if they have tens of thousands of computers, I'm guessing they can collectively afford some kind of hub office where they can just connect these things directly.
That does sound very reasonable. Here, let me see if I can find a... perfect picture. It's a little dim, but that's pretty much what it looks like. So Ian is by far the closest here. It's,
We were all laughing at this a second ago.
So it's called a point of presence. So it's not actually operated by AT&T or by Global Crossing or by Internet 2. there are other companies. The names escape them now, but they escape me. That is.
With Cisco and networks.
No. They make hardware. No, there's. They're not important in. Like no one's heard of them, but they run these big rooms with lots of cables in them, and AT&T they will put a cable in, and they will have one router that's theirs. It sits here somewhere, and then they will have like Internet 2. That's another one over here, and then if you want a link between the two, well, you pull a cable like that. Right. So that's a little short because, but you could easily go with say 3 feet. So it's likely to be 3 feet, 10 feet, something on this order, because they're in the same room, they're in the same rack probably. So that's how you make a link between global networks. And the same thing actually happens for UIC. So if UIC makes a link, like does some digging, or maybe uses someone else's, it's not a hose, what is it, like a little tube in the ground. Sometimes there are these plastic PEX, no, not PEX, some kind of plastic tube in the ground, and you can put a new fiber through it. They use pressured air and just put a new fiber, it goes through it, and then eventually they get to some point of presence like this. So now UIC has a fiber link going from here to one of these points of presences. At the point of presence, and I guarantee you there's several in the Chicago area, there's going to be pretty much every global provider is going to be available there. So now UIC can put in a few patch cables, and now they're connected to more of these. And probably University of Chicago is also going to have a link to there. So if University of Chicago is there, now UIC can put a link to the University of Chicago, and now we don't have to pay anyone to talk to the University of Chicago anymore, right? Because we have a direct private link, and that's actually how the whole internet works. So at the very top, none of the big providers pay anyone, but they all talk to each other because they have these little cables going between them. So it's all a big mess like this.
What's the difference between like a point of presence connecting like one point of presence to another, and the actual routers that are closely connected within the point of presence?
Points of presence typically are not connected to each other on their own. So they are not networks. They're just a big room. They might have like a fast Ethernet network inside, but there's no point in connecting points of presence. They're connected by all these other networks.
I think she means like the router in those rooms. Like what's it between them and the BGPs?
Oh, yeah, I see.
Yeah, the BGP router and the routers you see in the point of presence that connect.
They are the border routers. So you put your BGP router in points of presence like that.
Oh,
it makes sense.
okay.
So then you have, so the Internet 2 and AT&T and UIC, they're all in that place. And they just have little cables between their routers, between their BGP routers. And then, of course, it goes from here. If you're AT&T, now you have, so there's your BGP router in that room. And then there's tons of other rooms like this, and you have a little router in each one of them. And then inside of here, you got a few tens of thousands of other things. And it goes like all over the place. Right. So they have their own mess to deal with inside of there, but we don't have to worry about it. We just have to say, okay, AT&T, you deal with this one, and the Internet 2 gets to worry about this other packet. Right? So fortunately, we have some abstraction here, because the Internet is just hideously complex, and no one knows the whole topology. I mean, it's just not knowable. It's one of those, who was it that said that? Was it Cheney? The knowable knowns? No, that was Clinton, I think. What was it? Anyway, so the problem here is that even the topology between the autonomous systems is not known. Nobody knows who's got links between everyone, because no one announces this. This is not something you need to tell anyone. You just say, okay, yeah, I provide service for OSNet here. This guy says I provide service for him, and then AT&T tells us that, yeah, okay, if you want to get to over there, you can use me. It works that way, but they don't say anything about what's inside, and they certainly don't say that they have a link to the Internet too. Or they could. Maybe they do. But, so they don't, not much is revealed, and even researchers that spend their whole career trying to figure this out, they don't get it right. Yeah, they have estimates, and you can send packets try to figure it out, but it's like a science of its own. Okay, we have a few minutes left. Let's do a little bit of something a little more simple. Let's get a connection going to a web server. Why not? Let's talk to a web server. Web client. So it's not very different from talking to a file, but we need to know about a couple of things, like how do we describe an address? Who do we want to talk to, right? And then how do we open up a network connection? So that's a socket. I think it goes in syssocket.h. That's pretty much it. So we want a socket. Oh, call it S. Why did I not call it socket? Yeah, that's the same namespace. If I call my S socket as well, it's going to get confused. So, okay, so I have to say, I want an internet socket, address family internet. I want it to be a sock stream. So I want there to be like a byte stream going here. I don't want to just send some chunk off and hope for the best. I want a guaranteed delivery in order, and so on. So this actually ends up being TCP. But there's sort of an abstraction level there, and I don't care about finer details. I'll let the operating system decide which protocol I actually use. But it's going to use TCP. I'm almost 100% sure. There are other alternatives, but TCP is really what happens. Okay, now we have a socket, but it's not connected to anywhere. It's a little strange that it's called a socket, but you can think of it like, okay, I put a socket in the wall of my program, and someone else has a socket in the wall of their program, and now we ask the operating systems to put a cable between the two, right? So now we need to connect it, but if I want to connect it, I need to connect it to somewhere. So I need a socket address. Call it address. Okay. So now there's a few fields in this. Actually, let's find that on sockadder.in. This is an excellent reference, beach.us. They have all sorts of good networking stuff, but this one is nice here. So we have the family, the port, the address. That's all. Okay, so family is this AF-INET. Port is the port number we want to talk to, and we want port 80, right? For HTTP, but it's in network order. Okay, so this is byte ordering thing. Network order happens to be the reverse of Intel byte order, so it's big endian. So you start with the high order byte, high end, the big end of the number. So there's easy ways to do it. So you say, so let's see, host to network. I want a short for 16 bits. So H2N has 80, so that becomes a network byte order short, unsigned short. The value 80. And this is, I can't defend this one. It's just a little leftover. Someone made a mistake 30 years ago. Okay, so now we need an internet address. So let's say we want to talk to Google. And we're not going to resolve this automatically this time. We'll do that next time. So I just grab the address itself. Okay. So now we have an address. This is the full address, right? So we say, oh, we want to talk to the internet, or it's an internet kind of address. So this can actually be IPv6 as well. That's the IPv6 address. That's actually starting to become popular now, but we'll go with IPv4 for now. The port we want to talk to, the address, the IP address we want to talk to, and now we can connect. So we connect our socket using the address, size of the address as well. So now we're hopefully connected. Let's see. You never know. Might as well do some error handling. Okay, so we're connected. Now we need to send a message to our web server, or a request, that is. So let's see. A request is going to go something like get. I will just get the root. That's basically the home page, right? And we go, and now it goes like this: google.com. So new lines are \r \n in HTTP for some reason. That's our request, and I want to send it. So actually I could do write too. I'll do send. It's just there's some flags you can specify, and it looks nice. It looks networky when you say send. Write works the same. We send the request, and we want strlen. How long is it? And then there's no flags this time. So I sent my request, and then finally we want to get the response. Say it probably will fit in at 10,000 bytes. Receive from the socket into buffer at most 10,000 bytes. No flags. I think you specify flags there too. I'm not 100% sure. Let's see. Yeah, some flags. We don't need any flags. And finally, let's print it out. Okay, let's see what happens. Some warnings. Doesn't look too dangerous. I forgot to declare, to include standard lib. Look at that. There's Google responding. So what happened? I got a header back saying, okay, I think I specified google.com in my host. Let's see. What did I call it? Web client. Yeah, I said google.com. And what does Google respond? Well, you know, google.com doesn't really exist anymore. It's really called www.google.com. So you want to go ask there. Okay, and then we got back a little, in case our browser doesn't automatically redirect. The browsers look at this status code here, the 301, and they know that that means redirect. So it's going to automatically look at the location and go to the next place. But in case your browser doesn't do that, it also outputs a nice little HTML page for us. If we have a few more seconds, I'll try talking to www.google.com too. See if we get a different response. Yeah. Okay. Got some more stuff, but it's not too impressive.
I got a lot more stuff.
What are you looking for to make it?
I don't know.
Unless your box.
Why is it so short?
Because we ran out of space.
Yeah, the buffers.
Oh, 10,000 bytes. I mean, this is not 10,000 bytes. Come on, this is like 70 characters across. There's no way. Something else happened. Oh, sorry. Of course. We talked about this last time. When you do a receive or a read, there's no guarantee how much you're going to get. Same as from a disk. You get whatever they feel like sending you. So Google, they send a long response of 10,000 bytes, let's say. But it's chopped up in packets. Every packet can only hold about 1,500 bytes or so. So this is all that fit in the first transmission, in the first packet. Let's do another one. I'll just split them up like this.
Will they send you something to tell you that this is the last packet that you're going to be getting? So you know?
No, they don't send anything like that. But receive will return 0
Okay.
if it's finished. There, look, it continues. It's a very strange continuation. Oh, well, maybe not. Wow. Oh yeah. Yeah, it is a continuation. It says, if the protocol is HTTPS. Okay, so that looks right. So another packet came in with some more. It looks like it's not finished now either. So you'd have to loop over and print out the rest. But anyway, so here we are. That's all it takes to talk to a web server. Not much. Let's meet again on Monday then.